No.
This?
The gap, the energy gap.
This?
I think I have a question. This is also specs of distance?
No. The kx is momentum in the x direction. This is basically a way. These kinds of graphs are just.
So you increase the momentum and see that the energy has this.
These values, yeah. So, I guess the most important thing to take away in this is.
Moving the graph. Are you moving the graphene to make the momentum?
No, the momentum of the electrons traveling. So you have, conducting, you have electron transport. So you're trying to see the momentum of the electrons as they move along. I think the important thing to take out of this is just that physicists use these graphs to, I guess you could say, classify materials. Depending on what these kinds of graphs look like, you can say material, okay, this is an insulator, this is a conductor. In topological insulators, you have a duality. You have an insulator sometimes, a conductor sometimes. Depends where you ask.
What are theories predicting about this experiment?
In what aspect?
Like what when you generate the current, like what kind of phenomenon? You said.
Whether photocurrent or not?
Yeah, photocurrent.
This has been as far as we're concerned, the first research done on this.
No, but like what are theories predicting what the
I think when I left, because basically the idea was to go into this, like basically, let's play with this and let's see what happens. If we weren't even sure that we would get a photocurrent response, we weren't even sure that was going to happen. And so that was my summer. We did that and we said, okay, there's photocurrent response. But I think when I left, Nathan went back to the drawing board with theorists and like we're trying to figure out what should we expect. But I think it's important to maybe just play first and see if you do see anything else, and then, yeah.
Can you go back to the page with the knots?
Oh God. God,
No,
why?
Because I know I don't understand what's the invariant that this group of materials has the first knot and another group of materials. What's the invariant that you're using to?
Again, it's a topological invariant, and that's just you guys could probably teach me more about that. And it has to do with how the wave functions of the electrons are knotted. It's
But I don't understand what does it mean to have wave functions knotted.
Well,
what do you mean by that?
Cool.
The wave function is knotted somehow.
Yeah.
What does it mean? If I write you a function on the board, would you tell me if it is knotted or not?
Basically, as the electrons travel through momentum space, their wave functions knot. That means that the integral, they use integrals to represent the wave functions change, and the way they change makes them behave like they do. So we just have, what's cool is that you guys, I'm sure you can tell me more about topology, but what's cool is that there's a very physical consequence of these things, and that's just that there's this cool duality. Where it comes from and all these things, I don't know if I can tell you much about it. Yeah, sorry.
No, I'm sorry.
So, doing the research at MIT, could you give a summary of what a typical day of doing the research was like? How much hours was spent measuring, collecting the data? Like, what was that like?
Every day
doing
changed.
the experiments?
Every day changed. There was, for sure, at the beginning, I was just in a lab staring at someone, trying to figure out what the hell they were doing, what all these cables meant. And that's something that is just inherent to experimental physics. I guess I didn't really. The picture does not do it justice. Here, you had a bunch of cables that went out to a bunch of other spots, and you had like preamps and more cables and stuff like that. So definitely, a lot of it was just educating myself on what the hell was going on. Reading a lot of papers. Sometimes I spent an entire day in my office just reading or asking people questions. I guess the more exciting days where I was by myself in the lab. I definitely played with the toys by myself, and by the end of the summer, I knew how to handle all the optical setup of it, so I knew how to operate the laser without burning anything or breaking anything, and running. And a lot of it, I guess, to me, it's exciting because it's like, you try to study what's going on as you're taking measurements. But I guess if you look at it from an outside, it was like 5 hours of being in a cold room clicking things. And like, oh God, okay, that didn't work. Okay, that's not working. So like trying to figure out what's going on and what's wrong. 90% of the time, stuff just doesn't work, and like the setup is just wrong, and you work at it just hours trying to figure out what's wrong. It's very frustrating.
In data collection, how was the data collection?
Like I said, it was like hours of sitting in a chair in a cold room, manipulating or like for example, you collect data and then you see it's like crappy data. You're like, okay, let's fix that. So you go over here and you twiddle with the optics and you say, okay, the laser's not working, da 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 da. And okay, let's
How did you tell the crappy from the real one?
For example, I guess I don't have that data here, right? But it's for example, we had like a straight week in which the photocurrent, here I show you a very nice peak. All this is very nice. We manipulated the data, but for example, we had like noisy stuff. Literally, all we saw for a week was this. So I was just, and we didn't know what was going on, right? There was a lot of things that happened, and we weren't sure. Somehow we fixed it. I can't. That was like traumatizing.
Did you visit Boston?
I was in Boston for 9 weeks.
I know, but you were talking only about the lab. Did you visit Boston?
Oh, you guys want to know my experience? Yeah, I partied. That was fun. Yeah. We actually, the program has like social components to it, so that they take us out. They took us on a boat cruise. They took us on field trips. They took us to an island once, and I did like mopeds. So I was like partnering the whole day, and then but we did stuff with the interns. We became really good friends. We go out. I guess I don't know if I'm allowed to say we go out drinking and partying, and it was fun. It was a lot of fun, and I actually became really good friends with a lot of these people at the end. I didn't picture them all, but they're all like super down to earth, cool people, and they love physics, and they're very excited about what they do. So I became actually pretty, and I still keep in touch with a lot of them. Like I email with them. So yeah, it was a good group of people. Thanks.
All right, thank you.
What? I don't know what you're saying. Do you want me to take it up?
Thank you guys for coming. Next week in the colloquium, we will have Robert, a graduate student, presenting what his research is going to be on. Maybe you could speak more about it.
I could, but I wouldn't.
But it's going to be a graduate student of mathematics here presenting for his, it's part of a requirement for his master's degree. He has to present on the research he's doing, so this will be his opportunity to do so.